going to talk about now is counting. You might think, I know how to count 1, 2, 3. But counting can be a little bit more complicated than that. Let's start out with the notation. This notation here, read as n of a, means that we're looking for the number of elements in A. Recall, set A is here, this is set B, and our universe is here. You might think that the number of elements in A are these 7. However, as we talked about last time, if the word only is not present, do not put it in there. So this is looking for the number of elements in all of set A, which includes these. So the number of elements in A is a total of 10, not 7. We might also be interested in the number of elements in B. If we want the number of elements in B, we would notate that as n of B. The word only is not present, so we're not going to put that in there. This is not looking for the number in B only, which would be these 3 elements. It wants all of set B. So the number in B is actually 6, because we include those elements that are in the overlap. This right here is asking for the number of elements in A intersect B. If you recall, the intersection is what the sets have in common, and that would be this region right here. So the number in the intersection is 3. Now something else we might want to take a look at. Recall what this symbol is for, linking A and B. That's the union symbol. So we're looking for the number in the union. Now remember, the union is everything. Everything in set A, everything in set B. So I'm wondering, to find the union, since it's everything in A, everything in B, could we just take the number of elements in A and add it to the number of elements in B and get our total? Well, let's check. The number of elements in A equals 10. The number of elements in B equals 6. So if we were to just add the number of elements in A to the number of elements in B, it appears that there are 16 total. However, remember when we found the union and we shaded to show the union, that was all of this. If we go and count up the elements in here, we see that we have 7 here in A, we have 3 here, and 3 here. So that's a total of 13. The left side, 13, does not equal 16 on the right-hand side. So we would be unable to just add the number of elements in A to the number in B and expect to get the union. Looking at this, do you think that you can figure out why the two sides are not equal? If you're thinking that we double counted some elements, you would be exactly right. Think about the elements that made up the 10 in the number for A. That was all of these. When we counted the 6 for B, that was all of these. So in essence, we double counted those middle elements. If you note, the number in the union, which is 13, is off from the addition over here by 3. And that's significant because 3 is the number in the intersection. If we want to balance this, we would have to subtract off that number in the intersection. Now the left side is equal to the right side. So what we find is if we want the number in the union, you can go ahead and add up the number in both sets. But if they have something in common, you need to subtract it just once. Because the intersection was counted when we totaled up A, the intersection was counted when we totaled up B, and so if we just add that up together, we're counting the intersection twice. In order to eliminate the double counting, we subtract it just once. It's like saying, hey, we counted the intersection here, so don't count it here. Let's take a look at another example. Now we're going to let our universe be the numbers 1 through 10. We're going to define set A to be the even numbers. We're going to let set B be the set of odd numbers. We're going to go ahead and construct a Venn diagram and place the digits 1 through 10 in their appropriate places. So, 1, 3, 5, 7, 9 over here in the odd numbers, 2, 4, 6, 8, 10 for the even numbers. Let's go ahead and find the number of elements in set A. The number of elements in set A equals 5. If we look for the number of elements in set B, that is equal to 5 as well. Let's look at the number in the union. Looking at the number in the union, if we look at the Venn diagram, we can count up between A and B, there is a total of 10 elements. Now wait a second, we just finished saying that if you want the number in the union, you cannot just add the number in one set to the number in the other set and expect to get the right total. But in this case, 10 elements in the union is equal to 5 plus 5. 5 elements for set A, 5 elements for set B. Why in this case does it work out that for the union we can simply add up the number of elements in each set? Well, again, if you're thinking because the intersection doesn't exist, in other words, the number of elements in the intersection is 0, then you would be absolutely right. If I was to take into account the intersection and subtract like I did before, essentially I'm subtracting 0, which we usually don't even show. In general, when we want the number in the union, it is okay to add up the number in each set. However, if they do have something in common, we will end up double counting this way. Because we counted the intersection for A, we counted the intersection for B. So to make things right, we have to subtract the number in the intersection once. This is what we call the inclusion-exclusion principle. Now make no mistake about it, the inclusion-exclusion principle held up here. It just so happens that the number in the intersection was 0. So as we said, subtracting 0 has no impact, so oftentimes we don't show it. So be careful, if you're looking for the number in the union, go ahead and add up the number in each set, but make sure if they have something in common, we subtract it so we do not double count.